Today, we're diving into number systems and how computers use bits to represent numbers. A number system is a method for expressing numbers using specific symbols, kind of like different languages for writing numbers. We'll start with familiar number systems and then explore how computers handle numbers in their own unique way. Let's begin with the decimal number system, which we use in everyday life. It's called base 10 because it uses 10 digits: 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Each position in a decimal number represents a power of 10. For example, in the number 123, the digit 3 is in the ones place, which is 10 to the power 0, equaling 1. The digit 2 is in the tens place, which is 10 to the power 1, equaling 10. And the digit 1 is in the hundreds place, which is 10 to the power 2, equaling 100. So 123 can be broken down as 1 times 100 plus 2 times 10 plus 3 times 1, which equals 100 plus 20 plus 3, totaling 123. This place value system is crucial for understanding how numbers work. However, computers don't use base 10 because their hardware relies on electrical signals that are either on or off, leading us to a different system called binary. Now, let's explore the binary number system. Binary is base 2, meaning it only uses 2 digits, 0 and 1. Each digit in a binary number is called a bit, short for binary digit. Just like in decimal, each position in a binary number represents a power, but here it's a power of 2. Let's take the binary number 101 as an example. The rightmost digit, 1, is in the 2 to the power 0 place, which equals 1. The middle digit, 0, is in the 2 to the power 1 place, which equals 2. The leftmost digit, 1, is in the 2 to the power 2 place, which equals 4. To convert 101 from binary to decimal, we calculate 1 times 4 plus 0 times 2 plus 1 times 1, which is 4 plus 0 plus 1, equaling 5. So, the binary number 101 equals 5 in decimal. Let's try another example. The binary number 1101. We calculate 1 times 2 to the power 3, which is 8, plus 1 times 2 to the power 2, which is 4, plus 0 times 2 to the power 1, which is 2, plus 1 times 2 to the power 0, which is 1. That's 8 plus 4 plus 0 plus 1, equaling 13. This shows how binary numbers represent the same values as decimal numbers, but using only zeros and ones. Computers use binary because their circuits can easily represent 0 as off and 1 as on. Next, let's touch on 2 other number systems you'll often encounter in computing: octal and hexadecimal. Octal is base 8, using digits 0 through 7. Each position represents a power of 8. For example, the octal number 23 means 2 times 8 to the power 1, which is 8, plus 3 times 8 to the power 0, which is 1. That's 2 times 8 plus 3 times 1, equaling 16 plus 3, which is 19 in decimal. Octal was used in early computers to represent groups of bits, but is less common today. Hexadecimal, on the other hand, is base 16, using digits 0 through 9 and the letters A through F, where A represents 10, B represents 11, C represents 12, D represents 13, E represents 14, and F represents 15. Each position is a power of 16. For example, the hexadecimal number 1A means 1 times 16 to the power 1, which is 16, plus A, which is 10, times 16 to the power 0, which is 1. That's 1 times 16 plus 10 times 1, equaling 16 plus 10, which is 26 in decimal. Hexadecimal is widely used in computing because it's a compact way to represent binary numbers, as we'll see shortly. Now, let's dive into bit representation, which is how computers store and process numbers. A bit is the smallest unit of information in a computer, representing either 0 or 1. Bits are grouped together to represent larger numbers. For example, 1 bit can represent 2 values, 0 or 1. 2 bits can represent 4 values, 0, 0 for 0, 0, 1 for 1, 1, 0 for 2, and 1, 1 for 3. 3 bits can represent 8 values, from 0, 0, 0 for 0 to 1, 1, 1 for 7. In general, n bits can represent 2 to the power n different values. Computers typically use groups of 8 bits, called a byte, to represent numbers, characters, or other data. For instance, a byte, which is 8 bits, can represent 2 to the power 8, or 256 different values, ranging from 000000000, which is 0, to 1111111, which is 255 in decimal. Let's see how a number is stored in bits. Take the decimal number 13. In binary, we calculated it as 1101. In a computer, this might be stored in a byte as 00001101, with leading zeros to fill 8 bits. Each bit is a tiny switch in the computer's memory, set to either 0 or 1. Why is hexadecimal so useful for bits? Binary numbers can get long and hard to read. For example, the binary number 10110011 is 8 bits. Hexadecimal simplifies this because 4 bits correspond to one hexadecimal digit. Let's break down 10110011. Split it into 2 groups of 4 bits, 1011 and 0011. Convert each group to hexadecimal. 1011 is 1 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1, which is 8 plus 2 plus 1, equaling 11, or B in hexadecimal. 0011 is 0 times 8 plus 0 times 4 plus 1 times 2 plus 1 times 1, which is 2 plus 1, equaling 3 in hexadecimal. So 10110011 in binary is B3 in hexadecimal. This is why programmers prefer hexadecimal for binary data. It's shorter and easier to work with. Let's wrap up with a practice example to tie everything together. We'll convert the decimal number 42 to binary, hexadecimal, and show its 8-bit representation. First, binary. Divide 42 by 2 repeatedly, noting remainders. 42 divided by 2 is 21 with a remainder of 0. 21 divided by 2 is 10 with a remainder of 1. 10 divided by 2 is 5 with a remainder of 0. 5 divided by 2 is 2 with a remainder of 1. 2 divided by 2 is 1 with a remainder of 0. 1 divided by 2 is 0 with a remainder of 1. Reading the remainders from bottom to top gives 101010. So 42 in binary is 101010. Next, hexadecimal. Group the binary 101010 into 4-bit chunks, padding with zeros to get 00101010. The first group, 0010, is 0 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1, which is 2. The second group, 1010, is 1 times 8 plus 0 times 4 plus 1 times 2 plus 0 times 1, which is 8 plus 2, equaling 10, or A in hexadecimal. So 101010 is 2A in hexadecimal. Finally, the 8-bit representation is 00101010, padded with leading zeros. This shows how 42 is stored in a computer's memory as a series of bits. In conclusion, we've explored the basics of number systems: decimal, binary, octal, and hexadecimal, and how computers use bits to represent numbers. Binary is the foundation because it aligns with the on-off nature of computer circuits. Hexadecimal serves as a convenient shortcut for binary, and systems like 2's complement allow computers to handle negative numbers.